This video is going to run through some properties of logarithms. Specifically, we're going to be looking at the product rule, the quotient rule, and the power rule for logarithms. I want to start by showing you where this product rule comes from. So let's consider two different expressions. M is log base b of big M, little n log base b of big N. What happens if I take the log of m times n? Well, based on these definitions, m equals log base b of m tells us that b to the m equals this big M. That's that logarithm in exponential form. We can do something similar with the other log. The base is b raised to this little n equals big N. So I can replace m with b to the m and this n with b to the n. So now I've got log base b of this product. When we multiply things with exponents, as long as we have the same base, we can add the exponents. So this turns into log base b of b to the m plus n. When you're computing a logarithm, you're trying to find the exponent. Log base b, b to a power, those are inverse operations. They undo each other, and we're just left with this m plus n. Going back to my original definition, this little m was log base b of m. This little n here, log base b of n. And so the basic idea here, if you have the log of a product, you can rewrite that as a sum of two logs. That's the important takeaway. And in short, the reason is logarithms represent exponents, and when we multiply, we add the exponents. So if we have the log of a product, we can write that as a sum of two logs. So there's my product rule for logarithms. We also have a quotient rule, and the quotient rule for log says if you have log of a quotient of division, we can write that as a difference of two logs. And that comes directly from the fact that when we divide, we subtract the exponents. So let's see how these properties work with some examples. Expand each expression into a sum or difference of logs. I'll start with log, it's log base 10, log of 2x divided by 3. Because this is a quotient, the 2x is being divided by a 3, we can use that property, the quotient rule, and rewrite this as log of 2x minus log of 3. And we can take this one step further because 2x is actually a product. It means 2 times x. And if we apply our product rule, we now have log base 10 of 2 plus log base 10 of x minus log base 10 of 3. Here's another example. Natural log of x times x plus 3 divided by y times x plus 1. This is another log of a quotient, so I'm going to break that up into a difference of two logs. Natural log of the numerator, xx plus 3, minus natural log of the denominator, y times x plus 1. Both the numerator and the denominator had products in them, and so now we can take this one step further. Log of x plus 3 turns into log x plus log x plus 3. Log of y, x plus 1, turns into log y plus log x plus 1. Now, since that second log is negative, that negative sign is actually going to apply to both of those logs when you use their product rule. So we're actually going to have to distribute this negative to both the log y and the log x plus 1. That gives me natural log of x plus natural log of x plus 3 minus natural log of y minus natural log of x plus 1. So one thing to notice here is that when you're dealing with products and quotients, anything that was in the denominator should be a negative log. It has to do with the fact that our negative exponents are in denominators. So both of the pieces that were in the denominator need to be negative logs. Anything that came from the numerator should be a positive log. That's something I keep in mind to help kind of catch mistakes I might make with negative signs. We also have a power rule for logs. The power rule says if you take log base b of an exponential, m to the n, we can rewrite that as a product. We can take that exponent, pull it out front, and write this as n times log base b of m. That's our third and final basic property of logarithms. So now, if we want to expand an expression into a sum or difference of logs, we can do the same thing we did before, but take it a step further. So I've got log base 2 of x to the 4th y to the 3rd over 5z squared. The x to the 4th y to the 3rd, that's a product, so it's going to become log base 2 of x to the 4th plus log base 2 of y to the 3rd. And then we're dividing by both the 5 and the z squared, so both of those are going to become negative logs. So minus log base 2 of 5 minus log base 2 of z squared. The next step is when we have exponents, like log base 2 of x to the 4th, we can take that exponent, that 4, move it out front and rewrite it as a product. So now I've got 4 times log base 2 of x. I did the same thing with the 3, plus 3 log base 2 of y, minus log base 2 of 5, and then I took that squared, and that became a minus 2 times log base 2 of z. Here's one more. Same thing. So if I use my product and my quotient rules, log base 5 of square root of x minus 2, and then that square root of x minus 2 is being divided by both an x to the 5th and a cube root of y. So when I use my quotient rule, I'm going to be subtracting both the log base 5 of x to the 5th and log base 5 of cube root of y. Now both the square root and the cube root can actually be written as exponents. Square root is the same as a 1/2 power. Cube root is the same as a 1/3 power. So we can use that power rule and finish by moving those exponents in front. So this expression expands to 1/2 times log base 5 of x minus 2 minus, brought the 5 out front, minus 5 times log base 5 of x minus 1/3 times log base 5 of y. We can also work in the opposite order and take sums and differences and rewrite them as a single logarithm. For example, if I have log base 2 of 5 plus log base 2 of 9 minus log base 2 of 3, the sum of logs is going to turn into log of a product. The difference becomes log of a quotient. So this turns into log base 2 of 5 times 9 divided by 3. 5 times 9 is 45. 45 divided by 3 is 15. And so this expression simplifies down to log base 2 of 15. Here's another one. Write as a single logarithm. 2 natural log of x minus 3 natural log of x minus 4 plus natural log of y. First thing I'm going to do is if there's any numbers in front of my logs, I'm going to move those back and make them exponents. So what I mean by that is this 2 natural log of x, I'm going to take the 2, and it's going to become an exponent on the x. So that expression turns into natural log of x squared. The second term, I move the 3, it becomes an exponent. Now I have minus natural log of x minus 4 to the third, and then plus natural log of y. As a single log, the two positive logs, we've got log of x squared, and then we've got plus log of y. That becomes log of x squared times y. And then the log that's being subtracted, that piece goes into the denominator. And so this simplifies down to log of x squared y divided by x to the fourth, or x minus 4 to the third. One more formula I want to give you in this video is called the change of base formula. So these properties of logarithms are product rule, quotient rule, power rule, really are kind of helping us work with logs that have the same base. We can only use that product rule, quotient rule to put things into a single log if we have the same base. It's also easier to work with some bases than others. And so on the screen, I have our change of base formula. Log base b of m, we can rewrite this with a brand new base by taking log of the new base of m divided by log with the new base of b, where b is the original base. So let's see how this works. And one reason the change of base formula is useful is it's going to help us evaluate logs using a calculator. So if I want to evaluate log base 5 of 7, this is something that I have to use a calculator to do. Because 5 to what power equals 7? Well, it's not going to be a nice whole number or even an integer negative number. Most calculators have two different log buttons. They have log base 10, and then they have a natural log button, log base e. But they typically don't have buttons for other bases. And this is where that change of base formula is going to be useful. I can rewrite this expression using base e, which my calculator does have an ln button. And I'm going to rewrite this as log base e of 7, or ln 7, divided by log base e of 5, or ln 5. Now I actually have buttons on my calculator. I can compute natural log of 7, and I got this number from my calculator, 1.9, etc. I can compute natural log of 5, and I got a number from my calculator. If I divide those two numbers, I get approximately 1.209. So this is telling me 5 to the 1.209 is approximately equal to 7. Let's do a couple more examples that involve all of our different properties. Let's let log base 5 of 4 equal a, and log base 5 of 7 equals b. Can we use our properties of logs to rewrite each expression in terms of a and b? So basically, I want to somehow take my expression, and the first one we'll do is log base 7 of 5, and I want to rewrite it so it has either log base 5 of 4, log base 5 of 7, or something else that I could potentially evaluate. So I notice my expressions for a and b both have base 5. So I'm going to start by using my change of base formula, and I'm going to change this to base 5. Using that change of base formula, I get log base 5 of 5 divided by log base 5 of 7. Log base 5 of 5 is 1. 5 to the 1 is 5. And according to the instructions, log base 5 of 7 is b, so I can rewrite this as 1 divided by b. Here's another one. Log base 4 of 35. So I'm going to start the same way. I want to change this to base 5. So this becomes log base 5 of 35 divided by log base 5 of 4. I know what log base 5 of 4 is. It's a. But let's see if we can deal with this log base 5 of 35. If I can turn that 35 into a 7, that would be helpful. And in fact, 35 is 5 times 7. So I can think of this as log base 5 of 5 times 7. Now I have a log of a product, so we can rewrite that as log base 5 of 5 plus log base 5 of 7. If we have the log of a product, we can rewrite that as a sum of 2 logs. And now all 3 of these logs in the problem, I can either evaluate or simplify using a letter. Log base 5 of 5 is 1. 5 to the 1 is 5. Log base 5 of 7, they told me that was b. And then in the denominator, log base 5 of 4 is a. So we can rewrite this expression as 1 plus b divided by a. The properties of logs can also help us evaluate expressions that we wouldn't be able to do otherwise without a calculator. For example, let's take a look at log base 3 of 45 plus log base 3 of 2 minus log base 3 of 10. I don't know what each of these individual logs are, and I would need to use a calculator to compute them. However, notice that we have the same base for all of our logs, and we have a sum and difference of logs. So we can rewrite this as log base 3 of 45 times 2. Sum of logs becomes a log of a product. And then that minus log base 3 of 10, that's a difference of logs that'll turn into log of a quotient. So this expression can be condensed into log base 3 of 45 times 2 divided by 10. 45 times 2 is 90. 90 divided by 10 is 9. And now this is something that I can evaluate. Log base 3 of 9 means 3 to what power equals 9, and the power is 2. And there's my final answer. This expression simplifies all the way down to 2. That was my last example. Please let me know if anything in this video is unclear.